Good evening, everybody. Hope everyone's doing well. I wanted to come on to record a lecture for Chapter 11. And so what I'll do, I'm going to introduce Chapter 11 to you, and then we'll work through one sample problem, and I will review what we cover in this particular recording, and we'll go over about 2 or 3 problems tomorrow, maybe 1 or 2 problems tomorrow, and talk about Chapters 10 and Chapter 11 together. To talk about the differences and the similarities between the two techniques. So again, Chapter 10 was independent measures design, and Chapter 11 is a repeated measures design using a t-statistic. And so we'll talk about the two, the advantages of one, the disadvantages of the other, and how they compare with one another. So I'm going to cover very briefly Chapter 11. We'll go over the premise, the assumptions, and the logic behind these two tests. I'll go through an example today, and then it should give you a pretty good idea of what we'll be doing for the exam on next week. So our exam next week will be on the 19th, so April 19th. I'm going to try to record a few lectures so that you can view the lectures, and then I will review those when we get into class. So just be mindful of that. We still have a few chapters to go. I want to at least cover 12, 13, and 14. 12, 13, and 14 for the rest of the semester. So I'll play around with recording videos, and then also we'll have some in-class work to solidify what was covered. Okay, so I'm gonna share my slides, share my screen with you rather, and then we'll get started. And while I'm doing this, let me also stop sharing. I'm going to do something really quickly before. Let's do this. Okay. All right, so let's get started. Screen. Okay, let's do this. All right, so chapter 11. So we're looking at a t-test for 2 related samples. And what this usually means is we call this repeated measures design. And what this means is we are looking to, we're usually using one person or several people, and we're putting them through 2 different treatment conditions. So usually it's a before and an after. So say we have a group of individuals who are measured before a treatment or effect, and then they're measured again after an effect to see if there's any difference between their before scores and their after scores. And we're looking at the effect that the intervention in the middle had to do with it. Okay, so we want to understand what the structure of this research study is. Again, we're looking at a mean difference, and so we'll talk about what that is. We'll talk about the effect size, the Cohen's d, the R squared, the confidence interval. We know about those things. They're going to be calculated a little differently, but not much. The same statistics are the same. The way we interpret them are all the same. It's just the way in which we're using the different statistics that we'll be using. Okay, we'll talk about pros and cons of repeated measures design and the independent measure studies towards the end. And again, we'll review this stuff on Wednesday. Okay, as always, you want to have a pretty good understanding of chapter 9 and chapter 10 because all of that is going to culminate into what we're doing for chapter 11. All right, so when we're talking about the repeated measures design that within subjects t-test, again, very, very similar to the original t-statistic that we used in chapter 9. We will not be using or pulling any variance like we did in chapter 10 because we had 2 separate individual populations. In this particular research design, we're only using one population, right? There's a group of individuals who were measuring their scores on a measure before or and after a particular intervention, right? Or we're looking at participants in two or three different, or maybe two different conditions, right? Maybe we're looking at them when they get a lot of sleep, right? So we're looking at their academic performance when they average, 6 to 8 hours of sleep a night, right? And then we measure them again when they're only getting, 3 to 4 hours of sleep. And we're looking at academic performance as a result, or at how the amount of sleep you get affects the sleep you have. Okay. But again, the repeated measures design, also known as within subject design, you have again two separate scores, but you're obtaining those scores for each individual in the sample. So if we had 100 individuals in our sample, we have two individual scores for all of 100 individuals. Okay. We're using the same participants in, again, both treatment conditions. And again, that makes it a little bit easier for us to recruit. So for independent measure design, if you need 20 participants, if you have two groups and you want 10 participants in each group, you're going to have to get 20 individual participants to participate in one group and the other. However, with a repeated measure design, you can use, again, if you want 20 individual scores, all you need is 10 people, because you're putting those same 10 people in one condition, and then you'll put them in another condition, and you're getting those two separate scores. Okay. There is, again, no risk that the participants in each treatment group differ significantly from each other because they have the same person. You don't have to worry about what we say in statistics, the individual differences between people. Since we're all unique, we're all going to score differently on measures. But when you're using the same person, that reduces the variance between the scores because you're using the same person, and that removes those individual differences that we see when we use an independent measures design. Okay. You can also test to see if people who are matched together or paired in same or some way agree on a specific topic, right? So, if you match them on IQ, you're looking to see how they respond to a particular measure of motivation, right? And so you want to see, do individuals with the same level of IQ have a similar way of motivation that they rate their motivation levels, okay? You can also use romantic partners, right? We know that they are compatible in some way, and so you use those romantic partners to again agree on or disagree on how serious and committed their relationship is. So you're going to look at that difference between maybe the male or the female in a heterosexual relationship or in a homosexual relationship, male and male, female, to see if there's any agreement on how serious and committed they are to their relationship. Okay, but again, since they're romantic partners, and they have some similarities in their preferences. Okay, so as a check, it says a research conducts a research study comparing two treatment conditions. It says and obtains 10 scores in each treatment. If the researcher used a repeated measures design, then how many subjects participated in the research study? Okay, if you think about this again, when you're looking at an independent measures design, automatically, if you have two treatment conditions, you're automatically going to know that you have 20 participants because you have to have 10 individual participants in one treatment condition and 10 in the other. However, with a repeated measures design, you're only using 10, and then the 10 will be used in one treatment condition, and then you'll give them a break and use them in the other treatment condition. So the answer for this one is 10. Okay. All right. So to get into the mix, of what we'll be doing, again, the structure of this particular t-test for repeated measures design, very, very similar to what we did in chapter 9. The only difference, and no pun intended, is we're going to be using different scores because we're looking at the difference between one treatment condition and the next, right? So if we have a group of individuals and they're going through one treatment condition and then they go through another treatment condition, we want to see what is the difference between those two times, right? So if you had time 1 and a time 2, you subtract time 1 from time 2 to see if there's any difference between those treatment conditions. Okay, so again, it's essentially the same as a single sample t statistic. Again, it's just based on different scores rather than just the raw score that we used in chapter 9. Okay, the difference score, I'll show you an example. It's just going to be x1 or x2 minus x1, and you want to see what that difference is, or that delta. Okay, so the sign of each different score tells you the direction in the change, and we'll talk about how that works, right? So if you go from x2 to x1 and you subtract x1 from x2 and you get a negative number, you know that there was a reduction, right, in the score. If there's a positive number, then you know that there was an increase, right? And so positive numbers mean there's an increase depending on what you're measuring, and any negative score means there was a decrease from time 1 to time 2. Okay, so you'll be mindful of that when you're looking at the signs of those different scores. Okay, the formula for the mean difference, because we have to find the mean difference is going to be the different scores. You're going to sum those different scores up, and you're going to divide by the number of scores that you have in your sample. So if you had a different score, sum of your different scores equals 100, right? You have 10 individuals in your sample, right? Then you divide that 100 by the n, which is 10, and you get a mean difference of 10, okay? So again, we'll talk through an example, and I'll show you how those things work, okay? So here's an example of a measure or a study. Talked about reaction time measurements taking before and after administering an over-the-counter cold medication. So they're looking at reaction times to see if the over-the-counter medication had any drowsiness effects, right? And so they were looking at alertiveness. They're looking at, how alert is a person before and after they administered this particular over-the-counter medication. Okay, and oftentimes, when an organization or a pharmaceutical company says that their drug is non-drowsy, sometimes it is, sometimes it isn't, but sometimes they have to check to see if it is the case or so. So in this particular study, you have 4 individuals, okay? 4 individuals, A, B, C, and D, and you're looking at their X1, which is their alertness or their reaction time before taking the medication. So you have 215, 221, 196, and 203. And now you're looking at an X2, their reaction time and measurements after the medication. And so you see for person A, so you're looking at person A, they initially had a before medication, their reaction time was 215, and their reaction time got better, right? So again, there was a reduction. So then you have a negative difference, right? However, for all the others, you see that there was a slowing down in the reaction time. So you have 221 to 242, 196 to 219, and then 203 to 228. So on average, there was a slowing of the reaction time for the over-the-counter cold medication. So again, you see the positive numbers here. That means that there was an increase from reaction time, and that's not a good thing, right? That's not a good thing because that means the reaction time is getting a little slower. Okay, so what all they did was they took the different scores in this far right-hand column here. They summed those all up. You got a total of 64. You divide that 64 by the number of participants in that sample, which is 4, and you get a mean difference of 16. Okay, so that's how you would calculate the mean difference. Okay, for a hypothesis test. Okay, so that was the main difference. For an hypothesis test, here is how you would structure your hypothesis test. So when they say to state your hypotheses and then state your alpha level, oftentimes for stating your hypothesis, you're going to, again, the null hypothesis would mean that your difference score, your mean difference score, is going to be equal to 0. Anything greater than 0 or less than 0 means that there's a difference between the two treatment conditions, okay? And so when you say the mean difference is equal 0, that's your null hypothesis, meaning that there's no difference between one treatment condition from the next, okay? So this refers to the mean for the entire population of different scores, right? Because remember, when we are using samples, we're going to be making inferences to the overall population. And so that's why we use the mu for the population, okay? The mean difference equals 0 does not say that everyone in the population will stay the same. it only says that on average, the entire population will show a mean of 0. So if we averaged all of the different scores for the entire population, we would get a mean difference of 0. Okay. The alternative hypothesis says, though, that the mean difference is not equal to 0, meaning that there is a difference between one treatment condition and the next. And we'll talk through an example, and I'll show you how that works. Okay. So here's an example. Again, we took a sample of 4 individuals from the population. In our sample, we see the different scores here located in this green column here. So you have a different score of 4, -2, 3, and 1. And so on average, right, that's 4, 8, 6, right? So the difference, or the sum of those differences, is 6. And so with that, you're going to then use that on average, and you divide that 6 by 4, you'll get a value, and that average will is what we'll kind of use to make the estimate for the different score for the population, right? So again, we're taking an average, right? We're taking an average here, and we're making an inference to the overall different scores for the population. Okay. Here are all the other statistics that we'll need to know and how to compute them. And I'll take you through an example. We're going to be using all of these next. So you have T equals MD, with the mean difference minus the null hypothesis would equal 0. And then you have your standard error, your estimated standard error for the mean difference. You're also going to have to calculate your variance of the different scores. And again, that's sums of squares over the degree of freedom. And the last thing you'll have to compute then in order to get your T statistic is the, again, estimated standard error of the mean differences. Okay, so we'll walk through each of these. Again, very, very similar to what we did in chapter 9. And we'll cover a few more examples when we get to class on Wednesday. Okay. All right, so just a learning check. It says a repeated measures design study with a sample of n equals 10 participants produces a mean difference of 5.5 points with a standard or a sums of squares of 360 for the different scores. It says find the variance and the estimated standard error. Okay, so I'm going to do that really quickly. Let me go back. I'm going to give you some time to write those down. Just pause the video to write those down, and I'm going to write them down myself so I'll have them. So we need to find 2 things. We got to find our variance, and then we need to find our estimated standard error. So we're going to write down our variance, which is going to be s squared equals sums of squares over degrees of freedom. And then you're going to find your estimated standard error for the mean difference, and that's going to be square root of s squared over n. Okay, so I'm going to go ahead and share my screen, and let's see, let's share my screen with you. Yeah. All right. Let's do this. Okay. All right. So let's do this. Waiting for the screen to load up for me. All right. Did not show on the screen. Let's see. Let's do this. All right. Let's do it this way. All right. So we got 2 things that we're calculating, right? We're going to be calculating our variance, Okay, it's going to be the sums of squares over degrees of freedom. And then you're going to be calculating your estimated standard error, the mean difference. And that's going to be square root of S of S squared over N. Okay, so let me do this. And so if you remember, we have two things that we're going to be using. So we have, in our example, we had a sample of N equals 10 participants. Okay, we had a mean difference of 5.5 points, and then we had a sum of squares of 360. Okay, 360. All right. So first thing we're going to do, we have our sums of squares. We have pretty much everything that we need. All right. We have our sums of squares. We got our degrees of freedom. Our degrees of freedom in this particular case will be n minus 1. So our degrees of freedom would be 9. Okay. So let's go ahead and get to it. Right. So we know we got s squared. We got our sums of squares is 360. Okay. 360. That's going to be divided by 9. So I'm going to go ahead and do that. That's going to be 360 divided by 9 gives me 40. Okay. And then we're going to do since we know our sums, we now know our variance now. So we're going to do our estimated standard error for mean differences. That's going to be 40 over, it's going to be 10. Okay. So then we're going to do 40 over 10, it's going to be 4. Okay. And then 4 equals 2. Okay. So in our example, we have, again, everything that we need. The mean difference was not necessary in this particular case. Again, we got our variance of 40. We got our estimated standard error of 2. Okay. So again, those things really, really easy to calculate. Again, using the values that you get. I'm going to show you an example and how we use how we're going to be using the mean difference and all that. We're going to walk through an example all the way straight through, and so that'll be helpful for you to kind of know how we solve for this one. Okay. All right. Let's switch back over really quickly. Let's stop sharing here. I'm going to move back to the slides. Okay. All right. And here, here. All right. So here's just a learning check. Okay. Here's just a learning check. I want to see if you can understand the research design and be able to look at how that might be done in the real world. Okay. So it says, for which of the following would a repeated measure study be appropriate? Okay. It says testing a group of twins for IQ, comparing boys and girls' strength at age 3, evaluating the difference in self-esteem between athletes and non-athletes, or testing students' knowledge in September and December. Which one do you think? Okay. Let you pause it, but it would be D, because in this particular case, you have two separate conditions, right? You're testing their knowledge maybe at the beginning of the semester, right? And then after the class, you're going to test their knowledge again at the end of the semester. Oftentimes, in these particular cases, you're going to use the same measurement tool. So you're going to perhaps maybe it's a math exam or math test or biology diagnostic test. So you'll test them before, maybe in September, and then you'll test them again in December after they have covered all the information. And so you want to see if they've mastered any of the concepts that they didn't know in December or in September, and see if they've gotten any additional knowledge in December. Okay. So again, that is what we use for a repeated measures design. Okay. True or false. Okay. It says a repeated measures study requires 20 participants to obtain 20 scores in each of the conditions being compared. Okay. And then it says, as the variance of the different scores increases, the magnitude of the t statistic decreases. Okay. So the first one, that one is going to be false. The second one will be true, or true, excuse me. First one is true. Second one is true. It says, in a repeated measures design, it says a study requires 20 participants to obtain 20 scores in each of the conditions. So if you think about it, they're having 20 scores in one condition and 20 scores in the other condition. And so since that is, you only need 20 scores, all you need is 20 participants. If you were needing an independent measures t-test, right, then you would need 40 participants, right? You're going to need 20 scores in one condition and 20 scores in the other condition. And so then you would need 40 participants altogether in an independent measures t-test. But since you're doing a repeated measures, you only need those 20 participants, okay? But again, each subject is tested in all treatment conditions, so only 20 subjects are required. And then in the second one, it says increasing the variance, and this goes with any particular test that we do. Increasing the variance increases the denominator and decreases the t statistic. So you want to decrease your variance, which then also will increase your t statistic, which gives you a greater likelihood that you'll reject the null hypothesis. Okay. All right. We're going to do, again, walk through an example here shortly. But again, the numerator of the t statistic, all that is measuring is that actual difference between the mean difference and the hypothesis population difference. And again, when we look at the null hypothesis, we know that that's going to be 0. So whatever our mean difference is, we're going to subtract 0 from that, and that will be the numerator. In the denominator, we're measuring the standard difference that is expected if the null hypothesis is true, right? And so we're just using the estimated standard error of the mean difference. And so that would be my denominator. And again, we're looking to get a higher t statistic so that we can reject the null hypothesis, okay? We're going to be using the same 4-step process as the hypothesis test that we've used since we began, the z-score, the z-test, okay? So we're going to walk through, again, those 4 steps: state the hypothesis, select the alpha level, locate your critical region, calculate the t statistic. And then in the last one, you're going to make your decision. Okay, so we'll walk through that with an example, and I'll show you how we do it. Okay, so here is an example. Okay, I'm gonna read the problem, and then we'll walk our way through. Okay, so it says, it's the night before an exam. It is getting late, and you're trying to decide whether to study or sleep. There are obvious advantages to studying, especially if you feel that you do not have a good grasp of the material to be tested. On the other hand, a good night's sleep will leave you getting prepared or better prepared to deal with the stress of taking the exam. So the question is to study or sleep, okay? To address this question, researchers started with a sample of 535 ninth grade students and followed up when the students were in 10th grade and 12th grades. Each year, the students completed a diary every day for 2 weeks, recording how much time they spent studying outside of school and how much time they slept the night before. The students also reported the occurrence of academic problems each day, such as did not understand something taught in class and did poorly on a test, okay, quiz or homework. The primary result from the study is that students reported more academic problems following nights with less than average sleep than they did after nights with more than average sleep, especially for older students. Okay, so again, this is a research study, and recently a researcher attempted to replicate the study using a sample of n equals 8 college freshmen and obtained the data that you see here. Okay, so academic problems for students after a night of below average sleep or above average sleep. So for the column that we see here, the above average sleep, Okay, so these are the number of academic problems after a night of above average sleep for all the participants. And then here are the academic problems for individuals with below average sleep. Okay, and then you have your different scores. So we're going to walk through this real quick. I'm going to write this out very quickly, and then we will get to it. Okay. So let me stop sharing my screen here, and then we'll share my tablet so that we can get to it. Okay. So let's do this. Share my whiteboard. All right. So what we're gonna do? Okay, I'm gonna recreate everything that we just learned. So we have participants. Then we got A, B, C, D, E, F, G, and H. We got above average sleep, so we're gonna go above average sleep, below average sleep, and then you have your difference. And then we're also gonna do a few other things here as well. Okay, so you got 7, 10, 8, 7, you got 4, 14 for C, 6, 13, 3, 11, 9, 10, 4, 4, you got 7 and 11. Okay, you get that one little dot over there. All right, so we have our different scores. We'll go ahead and put those differences in. So we got 3. And again, when you're doing your different scores, we'll call this X2, and this is X1. So with your different scores, you're going to do X2 minus X1. Okay, so that's going to be 3. That's going to be -1. That's going to be 10, 7, 8, 1, 0, and 4. Okay, so again, those are my different scores. All right, so now we're going to do the first step. We're going to state our hypotheses, right? So we state our hypothesis. We got step 1. Okay, so when we state our hypothesis, our null hypothesis is going to be this equals 0, and then our H alternative hypothesis is going to be does not equal 0, right? So that there is a difference. And then our alpha level for step 1 is going to be 0.05 or 5%, and we're just going to do a two-tailed test. Okay, so then we're doing step 2. Okay, step 2 is just locating that critical region, right? So we know that we have an alpha level of 5%. Okay, we know that our degrees of freedom for this one, so we got an N equals 8. So our degrees of freedom is just going to be N minus 1, which is going to give me 7. So what I'm going to do is I'm going to go to my T table in the back of the book, and I'm going to locate my critical region, my T critical, and my T critical in this particular case is going to equal plus or minus 2.365. I want you to make sure that you can figure these out, because again, that's going to be something that needs to be drilled into your head as we move into the exam. Okay, so you want to make sure that you get that. Okay, all right. So the next thing we're going to do, step 3. Step 3. Step 3 is just calculating the T statistic, right? So we're going to have to calculate a few things. One of the first things we're going to have to calculate is we're going to calculate our mean difference, right? So our mean difference, our mean difference is going to be calculated using our different scores, right? So we're going to calculate our different scores. We're going to do a sum. So a sum of D equals, that's going to be 32. Okay. And then what we're also going to do, I want to do our sums of squares as well. Okay. So I'm going to make some room over here. Okay. So then we're going to do D minus mean difference. And then we're going to square that. So it would be, let me move this over a little bit. That makes some room. Okay. It makes some room for this. So we're going to go D minus, then we're going to go D minus squared, because that's going to be our mean squared there, or our sum of squares. All right. So now, first thing we're going to do, we got to calculate our mean difference. So we got our difference score here. Okay, the sum. So our mean difference is just going to be 32 over 8. Okay, which is going to give me 4. All right. So in order to find my um, sum of squares, we're going to have to sum of squares equals. So we got to do my difference scores. So that's going to be 3 minus 4, okay? -1 minus 4, so on and so forth. So we're going to go ahead and do that, okay? So 3 minus 4 is going to be 1, or -1. This is going to be -5. Okay, it's going to be 6. Or it's going to be 3. So that's going to be 3. That's going to be 4. That's going to be -3. That's going to be -4. And this is going to be 0. Okay. So once you get your differences there, then you have to find you're going to have to square those. So this is going to be 1, 25, 36, 9, 16, 9, 16, and 0. Okay. And then all I'm going to do is sum that. So our sum of the squares is going to equal 112. So I'll bring that number down here. Okay. Having all that information, we know our degrees of freedom. Degrees of freedom for this one is going to be 7. Okay. So given all the information that I know and I've calculated, now all I'm going to do is I'm going to go ahead and do um, my variance first. Variance is going to be your sum of the squares divided by your degrees of freedom. So it's going to be it's going to be s squared equals your sum of the squares divided by your degrees of freedom. And that's going to give me 16. And if I wanted to go ahead and get my standard deviation, then my standard deviation just would be 4. Okay. All right. We also need to get my standard error, estimate standard error for mean difference. Okay. So that's going to be, I'm just going to keep it the same there, over 8. Okay. And that's going to give me 1.41. Okay. So all it is, you're doing the square root of 16, the square root of 8, divide those together by one another, and you get 1.41. Okay. Given all that information, now all I need to do is calculate my t statistic. All right. So let me go ahead and calculate that. That's going to be, I'm going to go ahead and write it out so you'll see it. That's going to be mean difference minus over standard estimate of standard error, mean difference. So that's going to be 4 minus 0 over 1.41, which is going to give me 2.84. Okay, so that is my t. T equals 2.84. Okay, so now knowing that I have a t value of 2.84, I have a t critical right here. of 2.365, right? I know that I will reject the null hypothesis. So my step 4, I'm just going to put it up here, step 4. I'm going to reject HO or H null, okay? So rejecting the null hypothesis. And what this says is that there is a significant difference between the uh, number of problems or academic problems that a student has the day after they get either a good night's rest or a below average amount of sleep, right? So sleep is really, really important because there's a significant difference. There's a significant, big significant difference in those who, when they get below average sleep, they have, again, more academic problems than when they get above average sleep, okay? So we're going to work that, okay? That's good. That's good. That's good. That's good. And the next thing I'm going to show you, before we get out of here, I'm going to go ahead and show you how to do a, let's see, let me keep my T value. I'm going to erase this stuff because I won't need it. Okay. I'm going to show you how to do your effect sizes real quick. Okay. But again, pause it if you need it. I'm just going to erase the stuff that I don't need, but I do need, let's do this. My T statistic, I'm going to need, so my T 2.84. I'm going to need my mean difference, which was 4. Okay. My sums of squares and my variance and my standard deviations. My standard deviation was 4. Okay. And I'm going to need my degrees of freedom, which is 7. Okay. All right. So again, when we do my Cohen's D, right? So my estimated D, we're going to do estimated D, estimated. Remember that that formula is going to be your mean difference over your standard deviation, which is going to just be 4 over 4. Okay. All that's telling you is that um, there's a one standard deviation effect, right? So meaning there's a large effect size showing that below average sleep gives you a significant amount of more academic problems than those who got above average sleep. Okay. So again, you want to get more sleep because when you have more sleep, you have less academic problems. Okay. So that's my Cohen's D. In order to get my R squared, remember that this formula is, it's going to be T squared plus degrees of freedom all over T squared. All right. So we got 2.84 squared over 2.84 squared plus 7. That's going to give me 807.07 over 15.07. And my R squared is going to equal 0.536 or 53.6%. Okay. So what this is saying is 53%, 53.6% of the variance is explained by the differences between getting below average sleep and getting above average sleep. So um, getting more sleep, again, explains a big deal for the amount of academic problems that a student has in college, okay? So again, or in high school rather, right? So getting more sleep, again, 53% or almost 54% of the variance that is explained in those academic problems is explained by how much sleep you get and the differences in below average sleep versus above average sleep. Okay. So again, that's how you calculate your 2 effect sizes. The second one, okay, the second one is calculated in this way. Okay. And I need to get my, let's see. I need to have my standard error. Estimated standard error, the mean difference. I think that was 1.41. Okay, let me erase these two. Okay, and remember when we're doing confidence intervals, we usually do 95% confidence interval. And so I'm going to calculate a 1% or 95% confidence interval. When you increase your confidence, you increase the range or the interval, okay, length or width, okay? So for this one, this is how you calculate confidence interval. Plus or minus t is estimated standard error for the mean difference, okay? So given everything that I know, I'm just going to plug numbers in, right? If I have a 95% confidence interval, again, we're using a t-test, right? So my t that I'm going to be using here is going to be 2.365. Okay, so that's the t I'm going to be using. All right, so I'm just going to plug the values in. You're going to get 4 plus or minus 2.365 times 1.41. Again, that was what we received from this problem, right? So we're going to be using that 1.41. So then you get equals 4 plus or minus 3.33. Okay, so then we'll just add and subtract, right? So you're going to get a confidence interval, 95%, and that's going to be from 0.67 to 7.33. I don't like the way that 7 looks. So I'm going to write another 7 right there. Okay. All right, so the actual 95% confident, right? 95% confident that my mean difference, my population mean difference is going to fit somewhere between 0.67 and 7.33. Okay. And again, my mean difference for my sample fits at 4, so it's somewhere right there in the middle. And so you're going to have that right there in the middle of the distribution, right? But I'm 95% confident that my t-value or the mean difference is going to fit in the middle of that distribution, somewhere in that distribution, right? If I were to increase my confidence interval, I'm going to increase my t-statistic, which would then also increase my confidence interval, right? So that interval will be a little larger, right? And with this, like we learned in the previous chapter, if your confidence interval does not contain 0, that means you have a significant difference, right? If it does contain 0, then that means that you do not, and you'd fail to reject the null hypothesis, right? But if it does not contain 0 in this interval here, then you would reject the null hypothesis, okay? So I'm going to stop right there. I think that's enough. We're going to stop there, and I'm going to cover the rest of them. We're going to review a few of these things. We're going to go over a few more problems so that you get an idea of how you calculate and repeated measure samples, t-test. We're also going to talk about the disadvantages and the advantages of a repeated measures design and independent measures design when you would use both or one or the other. And then we'll kind of review effect size as well, so that you get an idea of how that all works. Okay, so we're going to end here. Again, go over this video. Make sure you're working through the problems. If you need to pause, rewind. Make sure that you understand repeated measures design and be able to work out problems. We're going to go over through a couple, simple problems, and so be mindful of that as we move forward. Moving forward, we're going to use these times to, again, introduce, and then when we get in class, we're going to work on problems so that we can kind of get how things work, okay? We'll also talk about how and the why we use repeated measure design, because the why is so much more important than how you do it, because when we get into applying this to different problems, you have to know why you're doing it, because it makes everything make more sense, okay? But I hope you all have a great evening. I'm going to go ahead and post this to Blackboard, and I will see you all on Wednesday. Take care.